In this video today, I will be talking about acid and base catalyzed epoxide ring openings and the role of stereochemistry and regiochemistry in these reactions. So first, I'll go over the basic mechanism of an acid catalyzed epoxide ring opening. So with this basic epoxide in acidic conditions, first the oxygen is protonated by the hydronium molecule, which leaves a positive charge on the oxygen, which has 3 single bonds. And next, a water molecule can come and attack one of the carbons, and cleave the carbon-oxygen bond. This leaves a diol on this side of the molecule, and the water molecule was added to this side. So next, the positive charge will be eliminated when another water molecule comes to deprotonate the oxygen, leaving the end result of a diol. So next, we'll talk about regioselectivity in acid-catalyzed epoxide ring openings. So, in acidic conditions, the more substituted carbon is the electrophilic center, and it's where the nucleophile wants to attack. So as we did before, the oxygen will first be protonated, leaving a positive charge. And next, a water molecule will attack the more substituted side. So this cleaves this bond, and the alcohol is now on the right side, and nucleophilic addition happens at the more substituted carbon. Another water molecule can now deprotonate this oxygen, leaving you with your end product of a tertiary alcohol and a primary alcohol. Stereochemistry is also an important part of the epoxide ring opening reactions, but we'll talk about that later because stereochemistry is treated the same in both acidic and basic conditions. Now we will go over the basic catalyzed epoxide ring opening, which is much different from the acid catalyzed epoxide ring opening. Instead of the first step being used as protonation, now we have an alcohol to directly attack one of the carbons. Once this carbon-oxygen bond is broken, oxygen is left with an extra lone pair and a negative charge. So now an alcohol is already added, and a water molecule can come protonate this oxygen to leave you with the end product of the diol. In both acidic and basic conditions, the end result are diols. Regioselectivity and basic catalyzed epoxide ring openings work the exact opposite way than they do in acidic conditions. The alcohol shown in the previous mechanism will directly attack the molecule, but instead of attacking the more substituted carbon as it did in acidic conditions, it attacks the least substituted carbon. This leaves the original oxygen atom with a negative charge, and the alcohol is added to the least substituted side. The oxygen will then be protonated by a water molecule, and the end result will be a tertiary alcohol and a primary alcohol. Despite the differences in regioselectivity in acidic and basic conditions, stereochemistry and acid and base catalyzed epoxide ring openings are the same in that they both involve backside attacks. An SN2 mechanism yields anti-addition as shown in the product below. In this reaction, the oxygen is protonated, and instead of using water like we did in the previous reactions, methanol is now the new nucleophile. So because we're in acidic conditions, then methanol will attack the more substituted center and kick off the original oxygen. At the electrophilic center, stereochemistry is inverted, and because it's a backside attack, the methanol is added with a wedged bond, and then the methyl group that's left is shown in the front with a wedged bond. Another methanol molecule can now deprotonate this oxygen, and you're left with this as the final product. The nucleophile attacked from the back and pushed forward the methyl group, and the alcohol maintained its stereochemistry. Stereochemistry is only inverted at the electrophilic center and not at the original carbon that was not attacked. In basic conditions, stereochemistry is impacted the same way. The same molecule is treated with sodium hydroxide and water. The alcohol of the sodium hydroxide attacks the least substituted side of the molecule and kicks off the oxygen. This leaves a negative charge, which can then be protonated by water. This also shows anti-addition and has one alcohol in the back because of the backside attack from this sodium hydroxide, and the remaining alcohol in the front, just like in the original, in the side of in the carbon that was not attacked. It's important to notice that the stereochemistry was inverted because of the original molecule. In the original molecule, the stereochemistry is within the epoxide itself, and it's not only in the carbon backbone. We can see why this is an important factor by looking at this reaction with different stereochemical configurations. In this reaction, only regioselectivity needs to be considered because no stereochemistry is present. First, the oxygen gets protonated and leaves the Br with a lone pair, making it have a negative charge, which, because this is acidic conditions with hydrobromic acid, can then attack the more substituted electrophilic center and kick off this alcohol. So now there's a bromine, a methyl that was originally in the molecule, and an ethyl which was originally in the molecule. This next reaction shows the same reactant and reagent, but also in stereochemical configuration. The ethyl group is in the front and the methyl is in the back. But it's important to notice that in the product, the ethyl group remains in the front and the methyl group remains in the back, while the bromine is added in the plane of the paper, just as the alcohol remains in the plane of the paper. This is because in the beginning, the stereochemistry was not within the epoxide itself. There wasn't wedged or dashed bonds in the epoxide in the beginning. In the final example, there is stereochemistry in the original epoxide, so there is also stereochemistry in the final product because of the anti-addition. The bromine attacks at the backside, which pushes the methyl group that was originally in the back to the front. And the bromine now has a dash bond showing it's in the back, and the methyl is wedged. Once the oxygen gets kicked off and can be protonated, the alcohol is also in the front because, like we said before, the electrophilic center is the only point where stereochemistry can be inverted. The carbon that is not the electrophilic center maintains its stereochemistry. Just to clarify, like we said, without the stereochemistry in the epoxide, the alcohol will be added in the plane of the paper, and the original oxygen that's protonated will also form an alcohol in the plane of the paper. If the stereochemistry is in the epoxide, then the backside attack will show that the alcohol is added with a dash bond, and this methyl will be pushed to the front. Only the electrophilic center is affected. So now I'll just give you some practice problems and you can work through them, and on the next pages I'll show you the mechanisms and the products for each of the questions. This is the answer to the first question, in which the stereochemistry is in the epoxide. There is no regioselectivity because there is the same amount of substitutions on each side of the carbons. So the only thing impacted is stereochemistry, and because hydronium is the reagent, we're in acidic conditions. So first protonation happens, and after protonation, a water molecule can come and kick off the oxygen, leaving the original oxygen atom the original alcohol to be in the back, and the new alcohol inverts the stereochemistry with this hydrogen. So once it's deprotonated by another water molecule, it will remain in the front while the hydrogen is pushed to the back. For the second question, we're in basic conditions as the alcohol is the reagent, and there is no stereochemistry in the original molecule, in the epoxide of the original molecule. So all of the stereochemistry is maintained because now there is 2 methyl groups at one carbon and 1 methyl group at the next. But basic conditions favor the least substitution, so it will attack and stay within the plane of the paper. And then after protonation, the next alcohol is also in the plane of the paper. For the final question, there's stereochemistry in the epoxide as well as the carbon backbone. As you can see, the isopropyl group is in the back, and the epoxide is in the front. The hydrogen group is in the back, and the methyl is in the plane of the paper with the hydrogen. So also acidic conditions because hydronium is being used, so the first step is to protonate the oxygen of the epoxide. Regioselectivity is also considered here because even though it seems at first that both of them are attached to carbons, if you do tiebreaker mode, this carbon is attached to 3 hydrogens and this carbon is attached to 2 other carbons. So the water will act as a nucleophile and attack the more substituted side, kicking off the oxygen, which will keep its stereochemistry and be in the front. Another water molecule will come and deprotonate this oxygen, and that will leave an oxygen group in the back. And because it's a backside attack, this isopropyl, which was originally in the back, will be pushed to the front, and the hydrogen will remain in the plane of the paper. So just to go over a few key points, it's important to know that in acidic and basic conditions can both cause an epoxide ring to open, but the mechanisms are very different. As far as regioselectivity, acidic conditions favor nucleophilic attack at the more substituted carbon, and the opposite is true for basic conditions where nucleophilic attack occurs at the least substituted carbon. Even though acidic and basic conditions offer different mechanisms, the stereochemistry is much the same, because inversion only occurs if the original molecule demonstrates stereochemistry within the bonding of the epoxide, rather than only the carbon backbone. If it is only in the carbon backbone, then the nucleophilic attack in the product will be shown in the plane of the paper.